Chapter 2, Section 3, Continuity. Y equals f of x is continuous at x equals a if these three conditions are satisfied. Continuous at x equals a. F of a has to exist. The limit of f of x as x approaches a from the left has to be equal to the limit of f of x as x approaches a from the right. In other words, the limit of f of x as x approaches a exists. The third condition is the two things mentioned here in the first two bullets. Those two things that exist have to equal each other. On page 80, exercise 2, y equals x plus 1 over x squared minus 4x plus 3. The directions here are to find the points of discontinuity. We notice the denominator can be factored. And we're going to give this function a name. We're going to call it f of x. Since f of 3 does not exist and f of 1 does not exist, we say there are points of discontinuity at x equals 3 and at x equals 1, because for there to be continuity at x equals 3, f of 3 would have to exist. For there to be continuity at x equals 1, f of 1 would have to exist. F of 1 does not exist. Exercise 20 is a piecewise function. F of x equals 3 minus x if x is less than 2. F of x equals 2 if x is 2. F of x is x divided by 2 if x is greater than 2. A piecewise function, which is what this is potentially discontinuous. Where it splits. This function splits from one piece to another at x equals 2. Meaning there might be discontinuity at x equals 2. So going through the bullets for continuity. Does f of 2 exist? According to the definition of the function, f of 2, when x is this number, when x is 2, f of 2 is 2. In other words, f of 2 does exist. because it's 2. If this middle condition were not here, f of 2 would not exist, because we have f of x when x is less than 2 up here at the top. We have f of x when x is more than 2 down here at the bottom. If this middle piece were missing from the definition of the function, we would say f of 2 does not exist. But the way it's given, f of 2 does exist. The next bullet. The limit of f of x as x approaches 2 from the left would be the limit of 3 minus x as x approaches 2 from the left, which is 1. And the limit of f of x as x approaches 2 from the right would be the limit of x divided by 2 as x approaches 2 from the right, which is 1. Because these are the same, the limit of f of x as x approaches 2, period, is 1. The limit of f of x as x approaches 2 exists because it's 1. The limit would not exist if these right here, if these were different. The limit would not exist. But they're not different, so the limit of f of x as x approaches 2 does exist. There are two things that exist. F of 2 exists. The limit of f of x as x approaches 2 exists. But the third condition for continuity is not only do those things I just put a box around have to exist, they have to be the same number, and they're not, because f of 2 is 2, and the limit of f of x as x approaches 2 is 1. Those are not the same number. So right here, this statement right here, that's the reason that there is discontinuity at x equals 2. That is the answer to part A. That's the point of discontinuity at x equals 2. A discontinuity is removable. If there is discontinuity, it's called removable if right here in the yellow, if the limit of the function as x approaches 2 does exist, then even though there's discontinuity, we call it a removable discontinuity. The reason we call it removable is up here in the yellow. Number 22. F of x equals 1 minus x squared if x is not negative 1. F of x equals 2 if x is negative 1. The directions that define the points of discontinuity. So we say there could be discontinuity at negative 1. So bullet by bullet. Does f of negative 1 exist? F of negative 1 is 2. F of negative 1 does exist. Does the limit of f of x as x approach -1 exist? Well, if I'm on either the right side or left side of -1. On the right side of -1, this is f of x. This in the green is also f of x on the left side of -1. So for sure, this equals the limit of 1 minus x squared as x approaches -1. Because the function is the same on both the left side and the right side of -1. This is f of x as long as x is not -1. So we find this limit that I just wrote by replacing x with -1. That's 1 minus, this says square whatever x is. That's what x is approaching, so we're plugging that in. Now this negative does not get squared. So even though the limit of f of x as x approaches -1 exists, I can tell you it exists because it's 0, but f of -1, which is 2, and the limit of f of x as x approaches -1, that's 0. Those are not the same number. So we do have discontinuity at x equals -1. Here in the red is the reason for the discontinuity, and we're going to call it a removable discontinuity. I'm going to say that discontinuity is removable. We call a discontinuity removable when the limit as x approaches this number exists. And it does exist because it's 0. So discontinuity at x equals -1 is removable. Number 24. What's given is a picture that looks like this. Up here there's a hole in the graph. Down here there's a point. Horizontal hole. Some more horizontal. A point floating here. All of this graph here, curve, horizontal, isolated point, is a graph of y equals f of x. And we are going to indicate all the points of discontinuity. So I'm going to tell you there's discontinuity at x equals 1, right here, and here's the reason. Even though f of 1 exists, I can see from the graph that f of 1 is 1, because the point 1, 1 is a plotted point. So that's the first condition for continuity. F of 1 has to exist. The limit of f of x as x approaches 1 from the left is 2, because if we are very close to 1 here, but on the left side, very, very close to 1, on the left side of 1, the y value right there is practically 2. But the limit of f of x as x approaches 1 from the right is 1, because on the right side of 1, right here, very, very, very close to 1, but on the right, here, for example, at 1.01, the y value there is 1. And x is very, very close to 1, but on the right, y is 1. When these limits are not the same, the limit of f of x as x approaches 1 does not exist, because those are different. So this proves that not only is there discontinuity at x equals 1, it also proves that it's non-removable. It is a non-removable discontinuity. To be a removable discontinuity, the limit of f of x as x approaches 1 would have to exist. Part B, or actually we're still on part A. There's another discontinuity. It's going to be at 2. There's a discontinuity at x equals 2 because f of 2 does exist. I would say f of 2 is 2 because the point 2, 2 is a plotted point. That's the first bullet for continuity. F of 2 does exist. But the limit of f of x as x approaches 2 from the left is 1, and the limit of f of x as x approaches 2 from the right is also 1, because when x is very, very close to 2 on either side, when x is 1.999 or when x is 2.0001, for either of those x's I just said y is 1. You can see on the picture. When these are both 1, that means the limit of f of x as x approaches 2 is 1. So continuity. You need f of 2 to exist. Check. You need the limit of f of x as x approaches 2 to exist. Check. So why did I say there's discontinuity at x equals 2? It's because f of 2, which is 2, and the limit of f of x as x approaches 2 are not the same number. One of these is 2, the other one is 1. So here's the reason for the discontinuity at x equals 2. Notice the discontinuity at x equals 1 was for a different reason. And the discontinuity at x equals 2 is actually removable, because the limit of f of x as x approaches 2 exists. I think we'll do one more example for this video. It's number 30, which says f of x equals x to the third minus 4x squared minus 11x plus 30 over x squared minus 4. And the directions tell you that this function is discontinuous. At x equals 2. And the directions are to remove the discontinuity. At x equals 2. Well, the only way that discontinuity at x equals 2 can be removed is if the x minus 2, which is in this denominator, cancels with an x minus 2 in the numerator. Because then the reason we have discontinuity at x equals 2 is because f of 2 doesn't exist. This function as is f of 2 does not exist. F of 2 does not exist because it is not possible to divide by 0. So the directions can only be accomplished if there's an x minus 2 up here. And we can cross those out. Over here, I'm going to do some division, either long division or synthetic division. 1x to the third minus 4x to the second minus 11x plus 30. I want to divide by x minus 2, so I put a positive 2 here. 1 times 2 is 2. Negative 4 plus 2 is negative 2. Negative 2 times 2 is negative 4. Negative 11 plus negative 4 is negative 15. Negative 15 times 2 is negative 30. 30 plus negative 30 is 0. That means this numerator right there is the same as x minus 2 times 1x squared minus 2x minus 15. 1x squared minus 2x minus 15. So the function can be reduced, the extraction can be reduced to x squared minus 2x minus 15 over x plus 2. This function is the same as the original function, except, here's a big exception, the two functions in the purple and the red are the same, except this new one is continuous. At x equals 2. And the original is not. What we say we did was we removed the discontinuity at x equals 2.